The next presenter is the group consisting of Gichoke Mwaga and Okinyi and Wanjogu on the title being Irrigation Water Conveyance Losses Research.
Good afternoon, ladies and gentlemen. I'm here presenting this work on behalf of the team. I'd like to start off by saying this is a child that was conceived last year during the conference that we had last year. We thought that it was going to be like a rabbit and be born sooner rather than later, but it took a full 9 months for it to be born, so it's really a struggling infant in terms of what we have been able to do. Because I was told to be a bit brief, I'll just highlight a number of issues, just again to bring everybody into the picture about our water management challenges, particularly within the NIB system, starting off with the high pumping costs in Ahero, Nyala, high levels of precipitation, unpredictable flooding and drought, high conveyance and application losses, high mismatch between water demand and supply, inadequate drainage of excess water in some cases, inequity in water delivery, inadequate skills of the farmers and so on, that is captured from the NIB strategic plan. And because of those issues, NIB and University of Nairobi got into discussing these issues, which finally culminated into this project, whose broader goals are really to try and look at that specific objective there. Is can we reduce the amount of water that we are using in our irrigation schemes, and the rationale is presented there. How can we enhance equitable water distribution with its own rationale? We need to reduce operation and maintenance costs with its own rationale. Again, need to enhance production and profitability, and then to reduce environmental degradation. So these are really the goals and the rationale for them within the broader irrigation development context. But to move more specifically to our issue of the need to reduce water losses, irrigation efficiencies are very low, ranging from anywhere from 30 to 70% of that conveyance loss, and that has implications in the scheme water intake. If you're losing 30%, you will withdraw more 30% more water. It has implication on operation and maintenance. You would have to pump that much more water, and at the farm level, you may not be able to get enough water. But now to focus on a much more smaller component of this overall study, which is the water loss issues. The goal is really to generate and enhance utilization of data and information on irrigation water management in ways that promote innovation and effective and efficient utilization of these water resources. Specifically, is to quantify water conveyance and distribution losses in 3 schemes, Ahero, Bura, and Mwea, and also to formulate strategies and plans to improve the performance of those subsystems. The key issues that are being addressed within this research program is to assess the performance and opportunities and constraints for improving that performance, identification of innovative solutions that will enhance the performance of water delivery and application systems, evaluation of technical performance of innovative solutions to reduce problems, evaluation of costs and benefits of improving the performance, formulation of strategies and plans for performance improvement, identification of investment priorities, and then moving on to the next issue of where will the financing resources come from. So if I go now to the methodology of what we have done in the last 2 months when the project has been operational, one of the things that we did is to try and characterize the schemes themselves. This is MIA is right here for those of you who are familiar with MIA. So we took unit command area here within the FIBA system of Mwea irrigation scheme, And we wanted to try to digitize the network, and we did that by using Google Earth, digitize the perimeter, the main feeder canals, the drainage canals, the roads, and so on. And the reason for that is because evaporation is taking and seepage are taking place from these canals. We needed to actually quantify what is the length and the width and even the cross-section of all these canals. So this is the part of the initial work. Once you have digitized that, then there's a whole question of now trying to transform that into GIS layers so that you can be able to compute the areas and the lengths. And the third thing was to try and see whether we can link a particular plot of land and link it to a canal, to a feeder canal, and that feeder canal is linked to a main feeder canal, and then to a branch canal, and so on. The rationale here is that ultimately, or rather not ultimately, but currently the problem that the water users associations have is that farmers somewhere in the schemes complain that they don't have water, and it becomes very difficult for the O&M office to decide where could the problem be within this fairly extensive irrigation system. By providing this information system, people will be able to say, oh, it's Mr. Njoroge. Once you know his farm ID, farm number, you can be able to establish that he's in this block, and therefore he's being fed by this feeder canal, which links to this main feeder, and then a certain branch canal, and so on and so on, and be able to be easily establish the water network. It's something similar to what Kenya Power does. Once you report that you have a problem with your power supply to your house, and they know which street you are on, they can be able to establish the grid network that brings electricity to your house, and therefore send technicians to the appropriate places. So we ended up characterizing these schemes. This is the characterization of a hair irrigation scheme. At that time, the two processes of digitization was taking place concurrently with the field work. So these units are actually numbered 1, 2, 3. But for those of you who are familiar with a HERO, you know that that is A, B, and this is C and D and so on. So those will be changed. The specific characteristics that we were trying to extract from this information is for a given unit command area, and as I say, I'm calling it U1 here, but it's actually unit command area A. The length of the canal end up to 6.7 kilometers. The area is 136 hectares, and the canal density is that you have 49 meters per hectare. And this is how this canal density varies in different sections of the canal. Why is this important? This is important because the higher the canal density, the higher your evaporation area and seepage area, and therefore the more water loss you are likely to get. This is the characterization of the Bura irrigation scheme. Again, we are calling them here units, where this is what was the forestry, Bura, Chowere, and so on. For those of you who are familiar with it, its characterization is as I indicated there. You can note here that you have now a much higher length of canals per hectare, and of course that will translate to more seepage losses. This is the FIBA system, but the only thing is it's running this way. For those of you who are familiar with seeing it the other way, this is the main canal. This is the Mia is here, Wamuru somewhere there. Its characterization is captured in that particular note. So the other part of the methodology we need to present is the loss assessment, and basically our focus was to try and establish how much water we're losing from the canal, and we were mainly three kinds of losses: seepage losses, evaporation losses, and operational losses. We did an inflow-outflow water balance method of quantifying how much water is getting into a particular reach and how much is leaving that particular reach. From that, we were able to get the two kinds of losses: what is evaporating from the water surface and what could be seeping down. On the other component was the operational loss that we picked up by trying to find out what were the leaking gates, and did a similar quantification to establish what those were. This is an illustration of what we specifically did in Ahero. The pumping station is right around here. At the end of that pumping station, we have gauging down there. Another one here, third one here. And one interesting fact here is that the entire scheme was not getting water at the time we were doing the study. It was only this unit and this unit and this unit. An implication of that is that, as you can see, water is being transferred over quite a long distance only to irrigate part of the scheme. And we'll be looking at the implication of that as we go on in terms of the way the systems could be better operated to reduce those losses. In Bura, we were not fortunate. We got there when the pump was down. But we nevertheless try to see how we can rescue, make productive use of the exercise by trying to see whether the water that was still in the canals, we could monitor the rate at which it was decreasing, which gave us an opportunity to apply the ponding method approach to assess seepage loss. Now looking at the Ahero results. This is what we would do at any one of those gauging sites. We will capture the profile, we captured then that in terms of the tabular format, calculated the velocities and discharge, and finally determine what the overall discharge of that particular cross-section is. In terms of finally computing efficiencies, we looked at the 8 sites we monitored. As you can see, site 4 was mainly used to determine how much water was being delivered to an irrigation unit, and the same thing with site 6, whereas these ones were along the main system. And as you can see, our irrigation efficiencies ranged, as you can see. We recognize that those seepage measurements needed to be extrapolated so that they can give us a bigger picture of what is happening within the scheme. To be able to capture that, modeling water balance model became our only way. And before we could model the system, we had to understand how the entire system works. So this is an illustration of a schematization of how the FIBA system works in terms of the hydrologic linkages. What I subtracted from here comes to this canal, it goes to the near system here. This is illustrated in more details in this particular section. So the idea was to try and find out where is water to irrigate a particular unit coming from, and where is its drainage water going. Because some of that drainage water ends up irrigating another field, like you can see in this particular section here. If we want to save water by lining this canal or improving the conveyance, we are not only benefiting this system, but this system also. So those are the hydrologic linkages we wanted to establish. The water balance model that we are then using is one that is applied at each one of these unit level. And the way it works out is we determine how much water has gone into this, has been abstracted in the feeder canal, the distribution canals, and the field canals, and then gets into the irrigated area. And there is also some non-irrigated area within that particular unit, which also receives rainfall. And I think this very complicated hydrologic connection, so I don't think I have enough time to explain in details, but for those of you who may want to engage in that, we can do that. But ultimately, the purpose is to be able to say how much water is being lost along this particular section, and this section, how much goes to the drains, and how much is lost at the drain, and if it is lost, how much goes to the groundwater, how much is actually taken from the drain and being used to irrigate part of the field. If we have non-irrigated area within the scheme, is some of its runoff getting into the irrigated areas, and so on. So it's much more comprehensive water budget. A preliminary analysis of the application of that model, which is part of now what we are trying to calibrate, is what we see here, where we're using to compute the irrigation water requirement, the seepage loss, and the evaporation loss for each one of these subsystems, and so on. Those results are then translated into what kind of efficiencies that are we having. For the few measurements that we have carried so far, we are noting that water irrigation efficiencies, as you would expect, are a little bit lower than they are for the other two subsystems. But more interestingly, we wanted to try and find out of those losses we are having, how much does seepage account for that loss, how much is from evaporation, and how much is from operational. As you can see here, in the case of where it has a very significant, about 35% of the water that is lost is due to operational losses. The implication, the reason for that is because gates are leaking, gates that are supposed to be sealed tight and are not delivering water to fields that are not supposed to be getting water, allow quite a substantial portion of that water to go away. There is also a lot of water that is lost in terms of filling and emptying the canal. And I would like us to, at some point, interact with the SRI group to try and look at the implication of alternative wetting and drying on the way the canal system will have to be operated, and what will be the implications on the water losses resulting from that. The other place was again in Ahero, where there was also a substantial loss associated to operation, operational losses. And again, there it was because of the long conveyance, a lot of gates that were leaking into fields that were not being currently irrigated. Seepage in Mwea was a little bit lower than the others, mainly because of a large number of canals that are irrigated at that point. What we are gearing for now is to undertake a number of simulation experiments. First of all, to calibrate our model as we collect more and more data on conveyance losses. But secondly, once we have calibrated the model, we need to actually carry out simulation studies and look at what happens if we change the design slightly. What happens when we change the way we operate the system. And one example here is, for example, changes in cropping calendar. As you can see in the case of where we have this kind of a staggering cropping calendar, it means that there are sections when parts of the canals are dry. If they are dry, it means they have to be refilled again, increasing the operational losses and so on. And yeah, sorry for being too fast, but I hope I have been able to do this.